Okay, so good evening. This is going to be a lecture 6 today. Right, and we would be continuing our discussion on curves just for a bit, and then we'll start with surfaces today. So last time I had mentioned that we'd also be discussing some additional topics such as knots and links, just a very brief overview of what they actually mean. We are not going to discuss about it in depth, right? So mind you that nodes and links are very useful concepts, but which are derived from. So nodes and links are important concepts which have its origin in the field of topology. And since ours is a course on the very basic introduction to differential geometry, we are not going to touch the topologies of in this course, right? So what do we mean by nodes? So let's start with what we mean by nodes, right? So intuitively speaking, what we mean by nodes is, so a node in simple sense is a simple closed curve in R3 that cannot be deformed into a circle without breaking the curve and reconnecting it. So that's what we mean by a node, right? Intuitively speaking, that's how we understand a node also, isn't it? So in other sense, in other sense, we can say that a node cannot be deformed into a circle by a continuous process. Without passing through right? Without passing through a stage where it is not a simple curve, right? Where it is not a simple curve. Right, so node cannot be deformed to a circle by continuous process without passing through a stage where it is not a simple curve. So that's what the intuition behind what we call a node lies, isn't it? Now we come to the definition of a node. So we will just be providing definition. We won't go further because of since this is somewhat a convoluted topic, and we may not have the necessary background in this course to talk about this. So we'll just give a passing reference to these topics. So definition goes that it's a simple closed curve gamma in R3 is called unnoted. It's called unnoted if there exists a continuous function which is given by h, which maps from S1 set the Cartesian product of 0 to 1 to R3 such that h of S1 cross 0 is equal to gamma, right? And h of S1 cross 1 is equal to S1, and such that gamma t is equal to h of S1 cross t. Okay. And so this is a mapping, continuous mapping. Right? Is a simple closed curve. So if there does not exist such a function, h the curve gamma is called knotted. So let's go by the definition. So it says that a knot, so knot is initially we start with what is an unknotted curve. So a simple closed curve gamma in R3 is called unknotted if there exists a continuous function h, which is a mapping from S1 cross 0, 1 cross the closed interval 0, 1 to R3, such that h of S1 cross 0 is equal to gamma, and h, the mapping from S1 cross 1 is equal to S1, and such that gamma t is equal to h. The gamma t happens to be a mapping which is parametrized with respect to t. It is a simple closed curve, and if there does not exist such a function h, the curve is called knotted. So let's just try to draw interest using some illustration. Say we have say this arbitrary curve, but it's closed. So let's call it as gamma, and let it be in R3. And now, so this is at t is equal to 0. And now what we do is let at the end say we have some say circle, right, of some radius r, of course. And this is what we call as this is just S1. So it's a sphere parameterized with R. So if we can have a mapping from here to here, say we take some measure, say we have this, this looks to, so of course we would want to preserve the arc length, so let me write it something like this. So say after some mapping, we have deformed it like this. And then we also have made some bit of deformation, which makes it closer to a circle and then eventually circle. So this is at say 0.5, this say 0.75. So which means that we have a mapping, which continuously we are deforming this arbitrarily shaped curve and mapping it to a sphere, to a circle. So this is a circle. So since in this case we are able to define such a mapping, which is H, which takes us from this arbitrarily shaped curve, shaped closed curve to a circle, then in that case we can say that this curve gamma is unknotted. Now, and this is R3. Now let's say we have a knot-like structure. So say so the way we define a knot, right? So let's try to build any knotted curve. Mm, Say we have curves which are intertwined like this in such a manner. Right? Some intertwining is here, and let's call it gamma. And even as we try to unfold it, there is one intertwining which never goes away eventually. So there is some intertwining here, maybe some sort of intertwining. I'm unable to draw it properly, but there is some intertwining here which never goes away. Like even if we take from t is equal to 0, t is equal to 1, the mapping, so to speak, this knot, or we are unable to make it a circle or map it to a circle. Then in such case, we say that these are knotted curves. And as just to just as a piece of information, so knot is something what we call as a so knot is a it's topologically invariant, or it's topologically invariant. In the sense that even if we continuously and arbitrarily keep on deforming it, but the thing is that knot would never go away until we cut it, until we cut the curve and then so what do you call bind it back, right? So which means knot is something which is topologically invariant. Likewise, now let's move on to just discuss a bit about links. So we do not aim to comprehensively cover these topics. We just give a passing review, passing remark on this. So what do we mean by a link? So in a sense, let's say that if we have a simple closed space curve, and in itself, a simple closed space curve in itself is a circle. Right? Now, what I mean to say that, say this here is a simple, this one is a simple closed curve, and it resembles a circle because say after continuously deforming it, we are able to get a circle out of it, right? Just by continuously deforming in such a way, right? And what happens is that knottedness, the property, what we call as the right? So knottedness is a property that concerns how a simple closed curve sits in the ambient space. Right? So ideally what we mean to say that simple closed curve is homeomorphic to a circle. Right? It's homeomorphic to a circle. And notedness what it does is it concerns how the curve is embedded in R3. Right? Okay. Now when we talk about links,
Krishna,
so yes, yeah.
what is the meaning of curve is embedded in R3? Like how nottedness
Okay.
says that curve. Yeah.
Yeah. So what happens in knots? I'm sure like if you tie a rope to itself by making some twists and turns, then in a sense you cannot open it back and form a say you have a rope, something like this, right? You have a rope, then you have just made some convoluted crisscross within itself, and then made itself as a closed something, such like this closed network, right? Now even if you try to expand it, you will never be able to remove certain crisscross, which means that until you cut it you cannot uh, say take it apart, or you cannot just convert into a simple closed curve. So what happens is, so when we talk about notedness, it always implies that in R3, all how the curve happens, like uh, say if the curve did if such closed curve like in this, since it is unnoted, then you are able to easily define or easily map it to a simple just a circle. However, if it is a noted curve, you can never map it to a circle, which means that you will always have at the best certain embedding eventually. Since okay, in a sense, let me make things clear here. Say this curve is in R3. It will be like, so
Yes. Yes. Yes.
imagine this or arranged in some fashion, but gradually you are just bringing it down to just R2 because the circle lies in R2. However, in noted case, say if you look at this noted, even after as much simplifications as was possible, from the side, it would have some structure like this, right? Some structure. If you look at from this side, and as if just as an example, say this is in xy coordinates, xyz coordinates, and even if you try to make it flat and say eventually you are able to get it something, you are able to deform it in as best possible way, you could never remove those knots. And when you see this figure from say from the x-axis side, then of course this vertical direction will be z-axis here. Then you'll always find there is some extensions along the along the z direction. This extension, because of this knot, it will this is how it will appear from the side.
Yes. 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 Yes.
So that is what we mean that it is an embedding in ultimately how the curve is
Okay.
embedded in
Okay.
R3. This is just
Okay.
as a
Okay.
very
The whole
simplistic
R3.
view.
Okay. Okay.
Yeah.
Okay. Thanks.
Yeah. So that is what we are calling as how the curve is embedded. Because if it's a simple closed curve, the embedding is just a circle. So and it's
Okay.
just an R2 object. So there is where
R2
the
object. Yeah.
difference.
In XY
Yeah.
plane. In XY plane, yeah.
in
Okay.
XY plane. So from the side, you will just see it as if it's a line in X at
Okay.
as Z is equal to 0. Okay. Now about links, what we were talking was that links is always the interaction between two curves. So say these two curves are linked. And just to give a 3D view, what we can say that say we have this, and this curve say goes from inside and comes from outside. So this is what seems to be a link. Something like this. Yeah. So there is a linking. So this is curve 1 and this is curve 2. So this phenomena of the interaction between two different curves. So these are called as links, right? Links. These are the links here. And even this is a topological invariant. Say any object will have, you cannot say separate both these curves without cutting them. So the more linking it has, the more convoluted it becomes to separate both the curves. So it would involve much more cuts. Now, say for example, this is in a sense is done in such a way that unless you cut it here in at least one of them, you cannot cut it, right? Unless say
Yeah,
you
yeah.
once, yeah, then only you can separate it. However, say you have this node here, I mean this link here. Uh, so for example, just to show. Now, in this case, what you see is look at both the situations. Here, curve 1, let me call this as curve 1. This is as curve 2. So here, curve 1 is passing over curve 2. And at this location also curve 1 is passing over curve 2. So do you think you can separate both of them without cutting it? Or will it require cutting?
I think it will require cutting.
Now look at it carefully.
Like
And
both
sorry,
the curve.
yeah, look
It's
at
like
it.
previous. It's like previous case.
No, here, I mean, that's the distinction here. So that
Okay,
is
yeah.
what it
You
is, right?
can. So in this case, you can just pull the right one and
Yeah, so it will be
take,
separated.
take it out, right? Yeah. Yeah.
Yeah, so that is what happens is in this case, linking number is 0.
Okay.
This is just for by visual inspection. We see that linking number is 0. And let us have an orientation of the curve like this. So this is the orientation. The So at this point, what happen is uh, at this point, there are certain standard notations for links at any link. Say if you have link like this at any point in this framework, so the left one or the right one or the curve which passes from right to left at the point of link, then this configuration is called +1 or sorry -1 link. And in the scenario when the left to right one is over the top of the right to left, then this scenario is called as +1. So this is the orientation. So let's look at in this case here. Say this is oriented. We are the parameter along the curve varies set t in this fashion, and in this also let's have some s varies in this fashion. So at this link here, right to left goes is over the top of left to right, isn't it? In this scenario, just look at here. Right to
Yes. Yes.
left
Yes.
is over the top, so which means there is -1. And at this
Okay.
state, yeah, in this state, what happens is
It is bottom to top from here.
Yeah, bottom to top, isn't it? So
Yeah.
here also it's the same. So this becomes also there is one more plus one here,
Mm-hmm.
right? Minus. So in this fashion, so in the sense that we have minus one here as well. So minus one, minus one. So the total is minus two. And linking number is the way we define linking number. Half of total addition of links. Summation of the links. So the individual linking numbers. So which means that we have half of minus one is equal to just minus one. And in this
Okay.
case, for the scenario on the right, when we take a look here we have, again, let me define an orientation. So this is an orientation. And likewise, this is the orientation. I'll just remove this so that curve 2. So when we take a look at here, the intersection point, so the right to left is over the top of left to right, which means the linking number is again minus one, isn't it? The right to
Yeah.
left is over the top. So here it will be minus one. And here, so this will go, so this is going towards this way. Let's specify the orientation here. And this one will be this way. So in this case, what happen is left to right is over the top of right to left. So left to right is over the top of right to left, because of which the linking number is plus one. So the total linking number, total Li is equal to minus one plus one is equal to 0. And half of 0 is 0. So only for curves which have 0 linking number can you be able to just pull it apart without cutting it. And so even, I mean, we can make very complex network of such curves, and then eventually, even if while still having the linking number as 0. So say, and the example of one such scenario is, say, when our, say, the wires of a earphone, they just get entangled. So the idea is to always find such ways of deforming that you are untangling it rather than tangling it furthermore. So we just have to look particular patterns and then pull it. So the goal should be just to find out ways in which we can pull it up. Otherwise, we can make it furthermore, so to speak. Visually, it will be linked. But the thing is, even if a very convoluted such entangle will have very small linking numbers. And many a time the linking number will be just 0. And if the linking number is 0, then of course you can just untangle it. So that is just one example of where do we see such the use of such linking numbers in, say, real life. Yeah, so I think with this we'll close the topic for curves. We'll start with surfaces today, and I think we'll be moving at somewhat faster rate and while discussing some of the important concepts rather than just going too much into it. So far we have been able to cover module 1. So that we have talked about definition, the arc length, parameterization, closed curves, level curves, parameterized curves, plane curves, space curves, simple closed curves, isoparametric inequality, nodes and links. Now, since we have lots to cover, so we would always try to make the sessions more useful by focusing on some of the important concepts and just passing definitions without going further into proofs and all. So for surfaces, we'll talk about definition, the smooth surfaces, talk a little bit about what do you mean by smooth maps, and of course discuss about tangents and derivatives on the surfaces. Then we have also normals and orientability, level curves, quadratic curves. These are just some simple types of curves which will just have give one example each. and then ruled surfaces, and of course surfaces are regular. And they are all such examples of curves and compact curves. Then we will just briefly mention about what is inverse function theorem. Then we would talk about maybe possibly in the next session about first fundamental form, what are the lengths of curves on surfaces, isometries of surfaces, the conformal mappings of surfaces, equiareal maps, and spherical geometry just little bit. So that won't be much of our focus right now. Then we will continue talking about curves on about surfaces, where we would be touching second fundamental form and the Gauss and Wintergen maps. So these are just very simple concepts, although they sound technically very uh, too much jargon. But then we'll also move to talk about geodesic and normal and geodesic surfaces. Briefly mention what is parallel transport and covariant derivatives, although our focus will remain more on understanding Gaussian curvatures and the rest and all the derived quantities. So, so that it typically be the flow that we are talking about. So today, if we'll try to give an overview about surfaces without delving too much into, uh, I mean, while keeping most of our focus to understand what are surfaces, right? Okay, so we will start with surfaces, and initially, let's first just begin. What do you mean by surface? Right. So mathematically speaking, although we have a very intuitive understanding of a surface, but in mathematics, how we define a surface is that uh, in loose words, surface is just a subset of R3 space that looks like a piece of R2 in the vicinity of any given point. Right? So when we talk about, say, for example, we always, of course, we would always talk about a spherical surface, right? So at any point, say, for example, consider this as the surface of an Earth. And while we are traveling on it or traversing over it, we always find as if the Earth is flat locally. Locally, the Earth, say this is the surface of Earth's surface. Locally, the Earth's surface appears to be flat. Right? So it means nearby any point, say P of where we are, say, right, where we typically say we are at a point or at an instant of time. So locally we feel as if we are able to see a neighborhood, and it seems that we are just staying on a plane, right? So what it appears that it's of course an R2, because plane essentially is in R2. And although this sphere is in R3, locally it is in R2, isn't it? So which means that sphere, the way we define sphere is there is some sort of a mapping locally from an R2 set to an R3 set. So that is the base, just a very say rudimentary level of mathematics to understand a surface, that it's some locally it's a mapping from R2 space to R3 space. So that's what we call surface essentially, right? That is how we build intuition, just the basic mathematical intuition. Now, before we say uh, try to give a somewhat rigorous definition of a surface, we first have to introduce to some set the concepts in set theory. So first of all, what do you mean by an open set? Right? So this is the thing that the so open set is, say, any subset or maybe a subset U of Rn is called open if whenever a vector is a point. So whenever a vector is a point in U, there is a positive number epsilon such that every point U vector in Rn within, say, a distance epsilon of A, within the distance epsilon of A vector, is also in U. So what we mean to say that, say we have a vector A in the set U, and if we have some say some other vector in Rn, which when U minus A is the distance between U and A, the Euclidean distance U and A is less than epsilon, then this implies that even U is an element of the U vector is also an element of U. So that is what we mean by an open set. So graphically speaking, say let's just illustrate here. So open set means, say say you have this set U here, some arbitrary set, maybe some arbitrary set U here, and A vector is a point here. And if U vector, right, U vector in this case, if the distance between U and A is less than epsilon, so if this distance is less than epsilon, then U vector is an element of U. Now let's, okay, in the interior of the set, it's still very obvious. Say at the boundary, say you have a vector A. You have the vector A, and you take a small some other point U vector, and if the distance between U and A is less than epsilon, then it says that U has to be an element of uh, the set U, capital U. Now, and you can have epsilon to be as close to 0 as large, right? Or whatever the situation demands. Now, for this to always hold, it implies that the boundary of U, the set U, must not be in U. So it means that we cannot have any points on the boundary of U, because if we had, say, a point on the boundary of U, even that also as a member of the set U, then of course any point to say we have the vector, I mean A vector on lying on the boundary, any vector even infinitesimally say outside, just say distance of epsilon on this side here, say on the top of this. So what happens is, although U vector minus A vector is still epsilon, but U vector is not an element of U. So in this case, what happens is, at the boundaries, we can never, so the thing is, at the boundaries, what you'll see that even if you take epsilon to be arbitrarily very small, there are many, of course, there are, say, infinite number of points which are not member of the set here. So this is what we call as the open set. So which means that the boundary of U must never be in U for the set to be called open. And any set which is not open in general is a closed set. So what happens is in closed set, we have in closed set, it is open set. So closed set, the way we define closed set is open set plus its boundary. Then becomes an open set. So which means that there are say A vectors in the set U, uh, and all, of course, U vector which are slightly distant from A. When, although if the distance is less than epsilon, the U vectors is not a member of the set, and that is possible only for closed set, right? So that's just a basic definition of U vector of the open set. And next we talk about what do we mean by continuity of a set. So continuity of a set, or just the concept of what is continuity. Right? Say if X and Y are subsets of Rm and Rn respectively, right? So what happen is, so these are the, and we have a map. So if our subsets and a map, we have F from X to Y. So this map is said to be continuous. Right? At a point A vector, A vector is an element of if points in X near A vector are mapped by F to points in Y near to FA vector. So in a sense, we mathematically, this, of course, this, let's use some notationally what we say, that if F is continuous at A vector, if given any number epsilon greater than 0, there is a number delta greater than 0 such that, say, U vector is an element of X and U vector minus A vector is less than delta, then this implies that f of U vector minus f of A vector is less than epsilon. Right. So this is what we mean by continuity. So this often we call as epsilon delta, say like epsilon delta equal inequality or something like that. We call this this proof, or maybe just epsilon delta relationship. To that's how we define a proof for continuity. Now, graphically speaking, what we mean by continuity is that, say we have a
Krishna,
set. Yeah.
so you said so if we map a point near A, which belongs to capital X,
Yeah.
to a point near f of A, right? So those so let's say the distance between the point in X, let's say
Yeah.
it is having some distance. That distance should be maintained when the point is mapped to Y,
No, no,
or
no, 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 no. This epsilon Epsilon and delta can be anything. Just the thing is, this should be very small.
Okay. Okay.
So ideally, what we want to say, we have a set X here, and there we have a point A vector, and say another point U vector, and we have a map F, and we have this Y set here, and this A gets mapped to this is F of A vector, and this is F of U vector. And if the distance between them is epsilon, then the distance between them, this one distance them is delta. Then distance between them must be epsilon, and it should be such that epsilon is equal to some constant into, or maybe epsilon is equal to some finite number into delta. That's how the relation goes. And then only we call it continuous. And if say happens that A vector are separated by delta and F and B, FA and FU are very far. Say if FA and FB are very far, say we have some distance, say gamma. And if say gamma is as a finite number, right? If gamma is a finite number, and although if these points are just very separated by a very small amount, then this function is not continuous.
Even though gamma can be written as a finite number into delta.
No, but this gamma is a finite number, although this delta is an infinitesimal number.
Okay, yeah.
Infinitesimal number is very close to zero.
Yeah, so it can never follow that relation that epsilon is equal to finite number into delta.
Yeah, but in this case, to make it gamma as a finite number, we really need this to be multiplied a very, very large number.
Yeah, very large number, yes.
Very large number, because of which it may not, because the thing is, to get a finite number from an infinitesimal number is as if you are multiplying it by infinity. Okay. So that's how it is, yeah. Now, graphically, you can also explain it in such fashion. Say, for any continuous, say function, we see that say on the x-axis, say we have x naught, and then we have x naught plus delta, and the graph here will be y naught, and then the other is y naught plus epsilon, right? So this is what happens for a continuous curves, x and y, or continuous function, if we call this a function. Now, if we are talking about discontinuous functions, then what happens is, even if you have 2 points, say x naught and x naught plus delta, here it will be y naught, and then you have a sudden large jump. Y naught plus very large number. Yeah, there is a sudden jump, even if the points are very, very closely separated. So these signals, that's why we call this function as discontinuous function. An example is delta function, or even say what we call as the unit function, the Heaviside function. That is also a discontinuous function, because till the time we define say some x naught, and then just from just any number which is greater than x naught, say x naught plus delta, this difference is huge, a very large number. This is an example of Heaviside function, and although we call it as 1, it looks like the difference is 1, but the thing is it's a very large number, because any slight increase from x naught, anything on the right hand side of x naught will directly jump, will undergo a huge jump. So that's why these functions are discontinuous. Right? And then there is a property called that the composites of continuous maps are continuous, in a sense that if we have the continuous function of another continuous function, they will also be continuous function. Of course, they sound trivial, but yeah, let's just accept it without proving. Okay. Now we talk about what we call as say in view of the definition of an open set. This is equivalent to the following. Say F is continuous if and only if for any open set V of Rn, there is an open set U of Rn of Rm such that U, the intersection with X, is equal to X is an element of X, and then F of X is an element of V. Right? So let's just go through this statement here. This is equivalent to the following. Say if F is continuous if and only if for any open set V of Rn, there is an open set U of Rm such that U intersection with X is equal to X is an element of X such that F of X is an element of V. So it's as if saying that you have this Rm space. Of course, this entire space is Rm, say for as an example, and then you have X or maybe U inside, and this set is say X, and then you have some say Y here. The set is Y, it lies in Rn space, and you have a small subset V. So F is continuous if and only if for any open set V. So for any open set V of Rn, there is an open set U of. So as if that's how you are able to map that the neighborhood of all the points here get mapped to the neighborhood of all the points here. So that is just a way of saying that's how we are just extending it, extending the concept of continuity for say higher dimensions. Because the thing is, these ideas we'll be using in while we discuss about plates, when we discussed about surfaces furthermore. Right now, let's we have one more definition, and what we call as the homeomorphism. Homeomorphism. So in homeomorphism, what we say that is this is a very important concept. And then a further advanced version of homeomorphism is what we call as the diffeomorphism. So in homeomorphism, what we say that if F, the mapping F from X to Y, if this mapping is continuous and bijective, and if its inverse map F inverse from Y to X is also continuous, right? Then F is called a homeomorphism. And X and Y are said to be homeomorphic. Right? So essentially what in homeomorphism, what we talk about is, it is continuity plus invertibility. So when we add these properties, then if a mapping is continuous and also invertible, then it's homeomorphic, as simple as that. So no need to be worried about all this stuff definitions. It has just this simple meaning. Continuity plus invertibility is what we call as homeomorphism. So the idea is that you can always go from one space to another without facing any issues. That it will be continuous and you can always move from space X to space Y and always get back another mapping from space Y to space X. And that is just the inverse. And the points in vicinity of in the vicinity of say a point in X will be mapped to points in the vicinity of that mapped point in Y. That's what we mean to say about homeomorphism. So in this case, say for example, if these points, if you have this map F, and if the set also allows going back, and if it's invertible, then this mapping is what we call it. Since it's already continuous, and if F also happens to be invertible, then it's homeomorphism. So that as simple as it is. And just slightly advanced version, of course, sounds slightly, but it's very tough to always ensure. That is what we call as the diffeomorphism. So diffeomorphism is
Krishna,
yeah.
can I ask a question?
Yes.
So in home before when you were defining that continuity of F, why the set and the subset U and V has to be an open subset? Why not it can be closed?
Okay, the thing is, most of these definitions we always define over open set, because in open set the issue is that the good thing is that you can always define the neighborhood of any point in the set, and the neighborhood will also lie in the same set.
Okay.
Going back, say for example, you have this a set U, which also includes the boundary. Say boundary is also included, which means that say U is a closed set. Then what happens is that, of course, since U is a closed set, then even the points on the boundary are members of U. So say A vector is an element of U and it lies on the boundary of U. Then we draw a small circle about this of radius epsilon, or maybe epsilon by 2. So that diameter is epsilon, right? So any point, so there will be this part. Maybe I'll zoom in. Let's just zoom in. So we have a vector here. Let's create larger just for zooming in. It does not mean that epsilon is large. Epsilon is small, still small, but I'm just zooming in. Say the radius is epsilon by 2 of this circle. What happens is only this part lies in U. So this one does not lie in U. See, I mean, so which means that so the set, we always would like to have open set because things are much more clearly defined. Say, which means that there is neighborhood about A, and although if the neighborhood happens to be in the immediate vicinity, but there are points which are not in the set U.
Okay, so open set, because in open set we can select a point A, but
in open set what happens is you can never, the boundary is not included in the set.
Okay.
So ideally the way we would define open set is like this: have a dotted line, and then all the elements inside are set of elements of say some set V, but this boundary is not included.
Okay, so if we select a point A on the...
So in this case, of course, we can never select any point on the boundary because boundary is not included.
Exactly, okay.
And any point
Got it.
Point slightly, say slightly away from the boundary we can always define that small circle because epsilon is infinitesimal. It can be as small and as large, but usually, of
Okay,
course,
got it.
as small. So you will always
Okay,
have
got it.
all the elements in that to be a member of the set. So that's the
Got it.
reason we always want to have
Okay.
a what we call as the close. So maybe I'll
So,
just cut this. This was a nice
so
figure
in
here. I
short,
put
in
it.
open set, we can never select a point on the boundary. So if we are not selecting a point on the boundary, then how can we say that if we define an circle of diameter epsilon, it will go outside U? Because we can never define a point itself on the boundary in the open
Yeah,
set.
the thing is, in this case, what we mean to see that all the points within this boundary, within this circle, will always lie in the set V.
Yeah, yeah,
And
yeah,
you
yeah.
can
Got it.
always tune epsilon. You can always tune epsilon such that it never crosses, it never enters the boundary. So the idea is we use that even between, say, even between 10 power minus, or maybe even between 0 point triple this, say 1 and 0.11, you even in between these two values, you have infinite points or infinite numbers, right? Infinite numbers. So you can always go as small as possible. And I mean, always define as small circle as possible, or what we call a small ball or disk as possible, and still the elements will lie in V. So that's what we make use of here.
Okay, thanks. Yeah.
Yeah, so that's what we are. Yeah. And now when we're talking about diffeomorphism, so diffeomorphism fundamentally is the mapping, if the mapping is continuous, so continuity of the mapping plus invertibility, of course, and also if the map is differentiable. Then we have then what this we call as the diffeomorphism. And in quantum mechanics, that's what you would see when you define a mapping function for the deformation. That deformation also has to be differentiable. Then only we are able to define deformation gradient. So when we talk about a body, you apply load. Say you have a body here, apply load, it gets deformed in some other shape. Then what we have is the mapping phi. So x vector is equal to phi of x vector. This phi is diffeomorphic. The reason is because we are often also able to define partial phi by partial x, which is we call as the deformation gradient. So that's where the word of this C, I mean, just as an example where we use this diffeomorphism. Right? So I think now we are in a situation where we can now mathematically, rigorously define what do we mean by a surface. So definition of a surface. Right? So definition of surface is that a subset S of R3 is a surface if for every point P vector is an element of S, there is an open set S, sorry, there is an open set U in R2 and an open set W in R3 containing P such that S intersection W is homeomorphic to U. right? So this is the main definition of, say, the subset S, right? Now, what we say that a subset S of a surface, or maybe a subset of a surface S of the form S intersection with W, where W is an open subset of R3, is called an open subset of S. Right? So open subset of S. And then we have a homeomorphism sigma, which maps from U to S intersection of W, right? As in this definition, is called a surface patch or reparametrization of the open set, of the open subset S intersection W of S, right? And then we have a collection of such surface patches whose images cover the whole of S, is called an atlas of S. Okay, so this was very lengthy. Let's go point by point. So we start with, say, a subset S of R3 is called a surface if for every point P is an element of the subset, there is an open set V U in R2 and an open set W in R3 containing P, such that S intersection W is homeomorphic to U, right? So for this, till this point, maybe I'll just break it down further so that we have very concrete graphical representation of what we are saying. So give enough space. In subset of S. Right, so let me just give enough space so that we can break it down further. Okay, so what we mean by subset? Say we have R3, of course, and then we define a subset S. Let's say this is the entire, this is R3 and this is the subset S. And if there is a point P vector here, and if corresponding to this, maybe I'll just put it on this side. So if corresponding to this, there is an for every point P, there is an open subset U. So say you have this is in R2 space, which means that you have X and Y. Maybe let's just call it X and Y. And you have some reason, say U. Right? So if for every P, let's slightly make it larger, and this is in 3D. So what happens is, right? And an open set in R3 containing P. So we have a small area of maybe let me use a different color. Maybe a small area of this, a small portion of the surface, and if you have this mapping from here to here, and this small one, the small portion of the surface is called W. So if there is a mapping from this R2 space to a small portion in RS, and if it happens at any point over S, so even if the point is here P, you can always define W and find its corresponding U. Then that is what, and if it is homeomorphic, that we can go from U to W and vice versa, then we call this as a surface. Then only this is a surface. So that's how technical the definition goes. So at every point in the subset S, if we can have a small open set which is homeomorphic to an open set in R2, then that S is called a surface. Right? They are just as we move along, we'll gradually grasp the meaning of this. So that was how we defined the surface, and that was using graphical say representatives so that it's easy to keep in mind. And then we go to the second part. A subset of S, surface S of the form S intersection W, where W is an open subset of R3, is called an open subset of S. Right? So which means that and again, so initially what happened is initially this W is not fully contained in S. Right? Of course, the thing is we are only talking about this W will not be fully contained, right? And that's the reason we only look for intersection between W and S, right? Now, a subset of surface S of the form where W is an open subset of R3 is called the open subset of. Right? There is just some saying that S intersection W, this is called as the open subset of S, nothing more. Now, a homeomorphism which maps from U to S. Yeah.
W
Yeah,
belongs to R3, right? And why?
Yeah, so let me just make it slightly more. Say, for example, this I have W and a portion of S and W. So this portion is what we call as, and of course there is P. This portion which is which is common to both W and S. This is S intersection W. Now we always need to find a mapping from U to S intersection W and vice versa. So there's just some technical, gradually understand why we take all this, do all this building, because to build such definitions, we had the people who may have say built all these theories, they would have started with simple definitions, and gradually what happens is you always fall into there are always some certain pitfalls where we need to go back and make the definition more and more robust so that all such pitfalls are avoided. So although it seems very convoluted, but gradually you see that we'll see the necessity of why we need to do this. The reason maybe just as a trailer, what we can say that if S is a surface, if S is a spherical surface, then what happens is we know that of course even locally it's only within infinitesimal region that we can see the surface to be flat. Only in infinitesimal region, which means that you have say rectangle of length epsilon and breadth epsilon. Only in that region we will see that it's a flat. It will appear to be flat. However, any slightly larger difference, I mean slightly say larger distance, you would never see. You would not see that it's flat, right? So in that case, what we do is we define W to be some local tangent plane. And will only certain neighborhood about the point P will be shared by both the spherical surface and the local tangent plane. So we map that small portion of the local tangent plane to the open set in R2, which is U. Right? So it is as if
So we are not even mapping U to S intersection W, but a very infinitesimal
Exactly.
point. Okay.
Very neighborhood of S intersection U. I mean, sorry,
Okay.
S intersection W. S intersection W is itself a very small, narrow region
Okay.
of the dimensions of just epsilon into epsilon.
Okay. Okay. That is S
Yeah.
intersection W. Okay. Okay.
Yeah. So that's the reason we had to build all this, because of course it's not true that you have it. It seems to be flat, but of course that flatness is for a very small amount, which is almost close to zero. So just to build that
Yes.
theory, we had to, yeah.
So if S intersection W infinitesimal area near point P, that will also be flat itself, right? When S intersection
It,
W is very small.
yeah, no. So the thing is, the intersection will be it will be flat only if we are considering as very small neighborhood about the point P.
Yes, 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 yes.
Because of course, along a spheric sphere, even if we move a little distance, say little distance from P, we never see there. Of course, there is curvature, or there is
Yeah,
you can
yeah.
feel the curvature. So which means that you can only move, mathematically speaking, something which is the distance which is close to zero but not zero. And it so happens that this, because the thing is definition has been made such that then even if the surface S happens to be plane, is perfectly flat, then this definition, I mean, holds, like it holds as it is. We don't have to make any, so to speak, assumption. Say if the surface as is a flat plane, then of course
It's in
W
R2,
and
R2, not
yeah,
in R3.
yeah, it will be still be in R3, but then W and S will be coincident, will be just overlapping.
And this will be coincident. Okay.
Yeah, if say S is a flat, if S is itself flat surface, then of course
Then it,
W we are the S intersection W will also going to be flat, and what we'll see that even W will just be flat. So it's like we are just we have two flat surfaces S and W, and what we'll see is that it's not only in the neighborhood where it is flat, it will be flat over the entire surface. Right, just I mean, just I think maybe I need better to draw it. So we have a surface S like this, it's flat, and we have point P vector, right? And then locally we have, say, some S intersection W, right? Then what we'll see is that we can always keep on increasing, or maybe it will so happen that not only in the neighborhood it's going to flat, but the entire, even if we take any larger W, or maybe the intersection, that will also be flat. So which means not only infinitesimal, it's flat over the entire surface. So in that circumstance, I mean, in that situation, what we're able to do is it's as if we are just mapping from U to S by just rigid body motion, right? If S is flat, then you don't need to have a very complex mapping, right? It will just be as if you take the entire portion of U and then rotate and tilt, and then it will become S.
some linear maps, yes.
Yeah, it just be linear map if S is flat. But and in that case, W also need to be as complex, because S intersection W is always going to be flat no matter what.
Oh, but in the previous case, to make S
Y-
intersection W to be flat, we need a small section,
Yeah, the region of
infinitesimal
intersection has
section.
to be very small. Yeah.
Very small.
Oh,
Okay, okay.
yeah, then only it will be locally flat, but no, never finitely flat. It will just be in the immediate neighborhood. So that's what.
So,
Yeah,
so
these are
Krishna, in the
very
previous case, will there
con
be a linear map? It won't be a linear map, right? In
linear
the
map will
previous
be
case.
from. Yeah, linear map will be from U to S intersection W, because then we are mapping
Yeah,
flat
exactly.
to
Flat
locally
to
flat.
flat. Flat
Yeah,
to flat.
flat to flat.
Okay, okay,
But then it will
okay.
be just linear in the differential form, not linear in the exact formulation form.
Yes, yes.
So it's the same in what we call, when we talk in quantum mechanics also, when we map a linear element, line element in the reference frame to a line element in the deformed flame, that deformation gradient happens to be a linear map.
Linear map,
but
yes.
Only in differential form.
True.
Yeah, so that's the same reason goes here also, same reasoning. Yeah. Now, let's look at what do you mean by homeomorphism from sigma from U to S intersection W is called a surface patch. So not surface path, it will be surface patch. Right? So is in this definition called a surface patch or reparametrization of the open subset S intersection of W. So what happens is these all small mapping. So it from here to reach this intersection, you will have some mapping, right? Some sigma. And what we'll see is that at every locally point, say in this Q, will have some different small mapping. This will have something, right? Maybe you can use the same subset U and map it to that one. So all the collection of sigmas which maps from this in R2 to that small locally flat region in R3, that will be called as a surface patch, because the mapping is valid only for a narrow region, right? It's not valid for across the surface. It will valid only for this narrow region. And likewise, you will have another flat. You will have all these surface patches, and when you combine all these surface patches, then only we get the curve that, I mean, the surface that we are seeing.
Yes, yes.
So I think, yeah. So it will all this locally flat, they stitch together to become the actual surface.
Okay, tell me, Krishna, one thing. Then if we combine the small sound patches, so in that case, the same U can be mapped to S intersection W, different lessons
Yeah, but
intersection
yeah,
W.
I mean, I mean, that will again depend on how we have taken sigma, but may or may not be. Sometimes we may have to take different U, and that will later
No,
we'll
we
say
can.
that
Can't we have a same U but different sigmas?
that's always possible. Then later we'll know what we call as the transition map, that which can map from one U to different U, and then there we keep on say having the same sigma but different transition maps which take from here to some intermediate U, and then we'll have the same sigma. So then we'll have another function called transition map, which just maps from U to different some intermediate map, and then have the same sigma. Those are all just I mean different just abstractions to do all that. So of course, since we have a transition map, of course, then all that we have is sigma tilde will be equal to a sigma of phi of U. So it will, in all the cases, the same U will go, and it's this transition map which will hold all that, which will say that, okay, you take this to some different U, and then from there we use the same surface patch to get every locally flat surfaces, locally flat regions in the surfaces. So this is what we call as a surface patch, or maybe we can just call it reparametrization, because later we'll see that we can reparametrize. We can move from one surface patch to another by defining something called as transitioning in between them. Okay. Uh, yeah. Okay. So that's what's how we can use the same surface patch but different transition maps to do all that. Now before and after, I mean, then what we have is the fourth point, which says that a collection of all such surface patches whose images cover the whole of S is called an atlas of S. That's just a definition. So all those surfaces consisting by stitching all those locally flat regions, then we construct a surface. So the collection of all those surface patches form an atlas. And I think in geography also we use atlas to determine or just as a model for the surface of the Earth.
Yeah,
Right?
book
So
of maps. Yeah, book of
yeah,
maps. Yeah.
so there also we'll do that. The thing is, we can never make we can never have a surface. We can never define or construct a sphere, a spherical surface, isn't it? We can only do it
Yeah,
by
yeah.
cutting small pieces of paper and stitching. So this word atlas comes
Mhm,
from
mhm.
there.
Okay.
Right? Okay, so we have this. Now what we'll do is we will maybe we should uh, maybe do one example, or maybe just I think since we are short on time, so what we will do is let's start entering into the actual theory of surfaces, right? And many of the things we will discuss uh, otherwise. And now let's just enter into the smooth surfaces area so that we are able to build the surfaces faster. Say what we mean by smooth surfaces, right? So in differential geometry, we will always be dealing with smooth surfaces. So smooth surfaces, on these smooth surfaces, we can use calculus. We use calculus to analyze surfaces, right? So in that case, we require, so we would want the view, right? We would want the function on a surface to be differentiable. So now let's start building what I mean by a smoothness of a surface. So smoothness of a surface, right? Maybe I'll just highlight this in red. Smooth surface. Okay. Okay. So far we have been we have dealt with what we mean by open set. So say first, if U is an open subset of Rm, then we say then a map f vector from U to Rn is smooth if each of the n components of f which are functions of course from U to Rn right, have continuous partial derivatives. Of order n, where n can be anything, any integer, any positive integer, of course, of all orders. So it means that n can be infinitely or infinite as well. So then the partial derivatives of a vector are then computed component wise. So for example, say if for example, if m is equal to 2 and n is equal to 3, then the mapping takes place from u, of course, u, which is an element, of course, u is a subset of say R2 to say R3, right? This is what's happening mapping. So in that case, f vector will be composed of Since f maps from R2 to R3, then f will of course have three components, f1, f2, and f3. Right? And then what we'll have is these are the components, but of course they will also have certain arguments. And say u, the component of u, uh, this one will compose of say any an element uv will be a vector of size 2, which is an element of capital U. So which means that f will be a function of f1 will also a function of uv, f2 will also a function of uv, f3 also a function of uv. Right? And then we define partial, then we define the partial derivatives of f vector as follows. So partial f vector by u is equal to partial f1 by partial u, partial f2 by partial u, and partial f3 by partial u. Right? And likewise, this one will be partial f by partial v, partial f1 by partial u v, partial f2 by partial v, and then partial f3 by partial v. Right? So these are just the, so what we are doing is we are component wise, we are differentiating with respect to u and v. And that's the same what we do even in when we determine the deformation gradient at any point capital X vector. So we also say differentiate the mapping function with respect to each of the components. So that's the analogy here. Now we will often use the following sort notations. Right? So partial f vector by partial u we'll just call as f vector and u as the subscript. And likewise partial f vector by partial v is equal to f vector and then v as a subscript. And likewise by u squared is equal to f vector uu and f vector u and then v is equal to f vector uv. Then partial of a vector by v squared is equal to partial FVV. So likewise, all these notations we will tend to use. And of course, there is one more remain. Partial square f by partial vu is equal to f vector vu. And it so happens that there is certain theorem which says that for a continuous function or for a smooth function, fuv is the same as fvu, right? For a smooth function. Right? So, which means that f vector uv is equal to f vector vu if f vector is smooth. Right? Now, which means that sigma vector, which was a mapping, what we call this homeomorphic mapping, which maps from U to R3, is also smooth. And we would only deal with smooth functions. Now let's properly define what we call as the surface patch. Definition of a surface patch. What does it say? So the definition states that a surface patch sigma vector from U to R3 is called regular. So we'll be using many of the terms which we had already encountered while studying curves, because ultimately surfaces are nothing but a network of curves, right? So a surface patch sigma from U to R3 is called regular if it is smooth and the vectors U vector sigma vector U and sigma vector V are linearly independent, linearly independent of at all points. UV element of the set U, and equivalently sigma vector should be smooth and the vector product sigma U vector cross sigma V vector should be non-zero. At every point of U. Right? So that is how we define the regular surface path. So the idea is that we always want to say obtain the basis vectors which we use to construct the surface itself, right? So what we do here is that any surface path is called regular if it is smooth and the vectors sigma u, which is nothing but partial sigma or partial u, and sigma v are linearly independent. At all points uv is an element of u, and equivalently we mean that sigma should be smooth and vector product sigma u cross sigma v should be non-zero at every point u. So that's what we mean by surface paths. Now let's just talk about one more definition before we wind up today's lecture, today's session.
Krishna, why the vector product should be non-zero?
Okay, the thing is, if vector product is non-zero, I mean, so the answer lies in the what we call as linear independence. If say sigma u cross sigma v cross, if it is zero, then this implies that sigma u is parallel to sigma v, right? Yeah. So which means that something constant is equal to sigma v, which means that we do not have
dependent.
Yeah, so that's the reason we want the vector product to be non-zero at every point.
Okay. Yeah, I got it.
Yeah. So let's look for some more definitions. So the definition here is about if S is a surface, an allowable surface patch for S is a regular surface patch sigma vector from U to R3 such that sigma vector is a homeomorphism from U to an open subset of S, right? And a smooth surface is a surface S such that for any point P vector is an element of S, there is an allowable patch, allowable surface patch sigma vector as above such that P vector is an element of sigma vector U and a collection A of allowable surface patches for a surface has such that every point of S is in the image of at least one patch in A is called an atlas for the smooth surface S. So the definition is quite long. Let's go again point by point. So say we already have defined what is a regular surface, and we all regular surface patch, and we also know what is a surface patch. Now say if S is a surface, an allowable surface patch. So here we are talking about what do we mean by what are the allowable surface patch, right? For S is a regular surface patch such that sigma vector is a homeomorphism from U to an open subset of S. So that is clear. So allowable surface patch implies that that surface patch should be a homeomorphism from U to an open subset of S. That's clear. Now, a smooth surface is a surface S such that for every point, P vector is an element of S. There is an allowable surface patch sigma as above such that P is an element of sigma U, right? So which means that if we have this P in element of S, then there is an allowable surface patch for which P is an element of sigma vector U, and a collection of all these allowable surface patches. So allowable surface patches are all those surface patches which are regular, and there is a homeomorphism from U to any open subset of S. So that's the understanding here. And if that an allowable the collection of all those allowable surface patches for a surface S such that every point of P is in the image of at least one patch in A is called an atlas for the smooth surface S. So it's like we want the atlas to be containing all those allowable surface patches, and any point in the surface S must be the mapping or maybe the range, the image of any at least one of the patches in the collection. Then we call the collection to be the atlas for the smooth surface S. So that is the definition here. There is a mouthful here, but the thing is, idea is very simple. It's just very much, I mean, the idea is very precise and very compact. So essentially, that's what there is in the definition. We don't have to worry much about the. So what we have learned here is we started with the regularity of a surface patch. Then we talked about uh, how like so how sigma should be smooth, and that the vector product of the partial derivatives with respect to the domain elements, right, U and V, it should be non-zero. And then we talked about what is an allowable surface patch, and then we arrived at the definition of an atlas. So these are just the points in the both definitions here. Yeah, so yeah, it seems we'll continue our discussion in the next session, where we will try to finish some more definitions from surface, and then we'll also finish the examples of surfaces so that we can very aggressively move on to understanding the first fundamental form and the second fundamental form, and of course the Gaussian mean and principal curvature. So that's the goal as of now. So I'll just stop recording.